You still got time, sort of. It's like, it doesn't count. All right.
Restart the recording.
I did. I'll restart it.
Yeah. That committed that we have to restart the recording.
All right. So what you can do is you can go to Node.js.org. And I actually might have it already installed in here, but let's just pretend like I don't. So you go to install, and it'll download the installer for this guy, 15 megabytes or so. So here on campus, that should only take a couple of seconds, up to a week.
Just the time just keeps increasing.
Does it? Oh yeah.
It went from 30 seconds to 2 minutes, 3 minutes.
I'm on FalconNet. That's why.
Get on Eden. It's the best.
Wait, I'm already done.
Really?
Yeah.
You took all my bandwidth.
Yep, I stole all your bandwidth. All
6
your bandwidth
minutes.
is belong to us.
Oh, here. Well, this.
Man.
Let's pause it, and then let's unpause it.
And it's done.
Oh, so you know that inflatable boat I was trying to do? It popped.
Not my fault.
The boat popped. No, but breaking the fishing rod was his fault.
No,
broke?
no.
It was a combination of them. It had to do with where you put the carpet. I couldn't shut my garage last night because the carpet was sticking out. So I went in and I tried to kick the carpet back in, which then hit one of the 2x4s, which then fell back this way and snapped a.
All your fault. All your fault.
All right, so let's see.
So by extension, it's your fault.
All right, let's re-download this again.
That's better.
All right, so what we're going to do is we're going to go ahead and put the Node server locally on our machine rather than, and you can do this on Windows as well. It supports both. And then we actually will have our API docs right here as well. And while I'm in here, let me just steal our code so we can use this. And I'm going to go ahead and open up a text editor. Okay, I'm going to change this to, it's already plain text, so I'm going to save this, and we're going to save it to the desktop, and we're going to call this server.js. Good enough. Okay, I'm going to go ahead and install Node, which I think might already be installed, but let's just see. Oh, maybe not on here.
63.1 megabytes. You have enough free space?
I have plenty of free space now.
Clear a bunch of stuff out?
I uninstalled WoW.
Well, there's like 40 gigs, at least.
Okay, we're good. I think on Windows, it'll give you actually an application you can double click on to launch. On Mac, it actually just installs it at the command line. Oh my gosh, there we go. All right, so let's just go here, then desktop, and there's my server.js, so I'll say node server.js. Oh, that's good. Oh, we don't have the Express modules. We have to go back and install a couple of those things. So we'll review. Just need a couple of them. And then I want to start talking about the asynchronous stream stuff today, provided the internet cooperates. All right, so the Node package manager comes with Node, so you already have this if you installed it. So we're going to do an npm install save express. Okay. Now our server's running. I think there was a couple other packages we might have to install when we get errors when we put some of the other stuff we had taken out. But we should have a running server now. And just as a quick reminder what our server currently does. Actually, what's the name of my, is it Sublime?
Yeah, it's a good text editor.
Let me actually close this guy. And then I'm looking for server. Oh, it just puts it at the bottom for no good reason. All right, it's probably a little small, right? View. Maybe it's references. Font size, let's go with 16 maybe. Is that bigger or not bigger yet?
I don't
See any difference?
Well, we'll know for sure when I say 36. All right, let's go to 20. Now let's just kill Sublime, relaunch it. It's not any bigger. Oh, well, that seemed to work. So who knows what editing that document is? Maybe it's just an excuse to use their editor. I suppose. All right, so this is big enough to read?
Yeah.
All right, so let's see. We have our, let's just test our simple hello world thing. So this should be localhost 8080. This is running off of our local machine. So we'll kill off nitrous here. And we'll say localhost 8080. Leave this page, and there's my hello world. So this is all running locally on your machine. Don't even need an internet connection to do this. Okay, so this should allow you to do some of the stuff that we were doing. So I guess with that in mind, if you weren't able to do the work over the weekend, just do it for Wednesday using the local copy of this. Okay, so having said that, I won't look at that then, so we can look at the stream stuff. All right, so we were, last time we were messing around with the JSON stuff, right? And working with JSON with the JavaScript tools is actually really simple. Unit testing. How many of you have heard of unit testing? Do you know what unit testing is? Where did you hear about it? Maybe software engineering? Okay, let me do something here. All right, we have this thing called unit testing. It's actually a very strange little situation that just happened in my head there. I was trying to say unit testing, and I felt like I wanted to spell Unix, U-N-I-X, but in my head I was trying to think, how do you spell eunuch, like Game of Thrones eunuch?
Like Ferris.
Yeah, so there was all sorts of things going on there. All right, so unit testing. Only one person here has ever heard of unit testing? All right. Oh, Abe, what's unit testing?
I don't know.
Just if we've heard of it, not if we know what it is.
Okay. Do you guys know what unit testing is? Yeah. You know what it is? All right, what is it? You can't answer what it is.
It's for ensuring that your software does what it's supposed to do, like your code or your method.
Okay, so I mean, what's the difference between this idea of unit testing and just testing your software yourself?
You write another piece of code that ensures that the first piece of code.
Okay, so unit testing is let's call it pre-programmed sets of testing methods that you can run over and over again to test your code for all sorts of different inputs. Kind of the idea of this is how many of you have ever dealt with the problem of when you're writing you write some software and then you add a new feature to it and now your software is broken? You've introduced a bug or something like that, right? And so let's say you've tested it with these 10 cases. And now you've introduced a brand new bug. You've added a new feature, and your new feature works flawlessly for what it's supposed to do, but it breaks these other 3. Okay. Well, you didn't necessarily have the ability to test those other 3 because you didn't remember all the tests you had run before. Our common way of doing this is what? You write a little function, and then you kind of throw some random inputs into the function to see what happens. Unit testing is more formal than that. Unit testing allows you to go through and create a series of tests that you want to run. So instead of remembering to do it one time and then hopefully you run the same test next time, you're instead creating a list of, I don't know, 15, 20, 30 tests, whatever, all sorts of things that might break your code but don't break your code. And then as you add new features, you're just adding to the list of unit tests. So at any point in time, you can just say, run unit tests, and it will test your code with everything it's ever tested with before, plus the new things you've added. Okay, so you'll instantly see whether things have broken since the last time. It's just a formal way of testing, nothing more. All right. Definitely something you want to do for a larger project, especially something that has a lot of features that are going to constantly be added to it. That's why it might have made sense that you guys talked about it in software engineering at some point. I doubt you did anything with it in software engineering, but that's the idea of unit testing. When you're working in large groups, and because you might not even be the one who wrote the tests, especially when you deal with data analysts who might be, whether they're quality assurance people for the company, they might be the one who's actually testing your code, and they're writing these unit testing. So they come back to you, these unit tests, they come back to you and say, okay, well, it failed these 3 unit tests. Now you can go and work on it. You can run the unit test yourself against it before you give it back to them so they don't scream at you saying you're stupid. All right, but I'm just going to shoot right past that. It's unimportant for what we were doing in here. Just figured I saw it on there. So, okay, so we want to look at streams in Node. And we've talked about these some up to this point. In here, we've dealt with input streams and output streams. And what would you say a stream is? Try to give a definition to a stream. Well, in real life, what's a stream? It's a water thing, people. Okay, what's water flows, right? Okay, down a path. That's a stream.
There's fish in it.
Okay, well, not always. There's not fish in every stream.
Oh, wow. You just can't catch them.
Huh?
I said a lot. You just can't catch them.
No, not. There's plenty of. I'm thinking about some streams right now that don't have fish in them. All right. So in computers, a stream would be what? Bits flowing over a network. Could be locally on your machine, streaming from one device to another device. Could be over the internet, whatever it is. Okay, so it's just a flow of bits is what a stream is. And we need to have ways of accessing these individual bits. And we've messed with it some in here with our buffered readers and stuff like that, reading things in, as well as our scanner, reading things in one at a time. Now, Abe, tell me what you know about the pipe.
The pipe.
All right, so that was a fun one. Yeah, so Abe, tell me about the pipe. How many of you have heard of pipes before as it relates to computers?
I think the last time we talked about pipes, that was with the slide with the rotating shaft.
An organization? Yeah, that was a good test. Okay, so idea here for a pipe. Let me just create a new tab here. And several of you have seen me do this before, but let's say that I'm doing something with GitHub. So if I type in history out here at the command line, it shows me all the commands that I've typed in recently, like the last 500 commands. So I can do, let's just do history. That's the pipe character. So we're not talking about the pipe character and everything, but this is how pipes work. So I'm going to take history. I'm going to pipe the output of history. Instead of it going to the screen like it just did. So if I just run history and I press enter, it just goes to the screen. Okay, but if I pipe it someplace else, so maybe I pipe it to something called blah.text. Oh, I'm sorry. Pipe it to something called echo, and then redirect that to blah.text. Now blah.text has all that stuff in it. Okay? But usually what you would do, pipe here, is you would pipe the output of history into maybe a search tool like grep. And let's just grep for anything that has the word git in it, for the GitHub stuff. So now I'm only going to get Git-related history stuff. Make sense? Okay. Similarly, if you only want to see things that have Java in it, now you're only going to get the Java stuff in it. Okay. So piping says take the output of one stream and pipe it into the input of another stream. Okay, so instead of history, which by default goes out to standard output, that's the standard output stream, which is in this case our screen. Instead of that, we are piping that input into the input stream of this program called grep. Okay, and this program called grep is then takes a single input, which is something to search for, and it then sends the output to standard output. I can then also pipe that to echo blah, pipe it to echo. So echo is just a command that takes in something and just echoes it to the screen, so we're not going to see a whole lot of difference here. Oh, actually, it's interesting. Since we didn't give it anything from the command line, no, echo won't do this. Pipe it to cat, yeah, that's it. So cat will throw it out to the screen, and then we can redirect cat to blah.txt or something like that. So now if I look at blah.txt, we see that here's the output of those things. So punchline is, what are pipes? Pipes are our means to redirect streams into other streams. Okay? Means by which we redirect streams into other streams. Okay? Okay, so we'll talk about readable and writable streams. Duplex, so we're just going to kind of fly through this. Let's go basics of streams. We've already dealt with reading files. Let's talk about compression a little bit. What is compression? We've all dealt with zip files and stuff like that before, right? So if I want something, I can take the output of a file. I think I have gzip on here, don't I? Okay, so I can take, for instance, more.blah, pipe it to gzip. Dash h. We can do blah.zip. So I'm going to do cat blah.txt, pipe the output of that to I need to create a new one. Save or restore. Well, if I do a -c, that's going to go to standard output. And then just redirect to blah.zip. That do it? Yeah, that did it. Yeah, let's look at that. There's my zip file. So there was a good example of piping. So we cat is concatenate. So we're concatenating onto this current stream blah.txt, piping the output of that instead of onto the current output stream into a program called gzip, which zips stuff, and giving it the -c flag, which says output to the command line. Redirecting that into a file called blah.zip, which is actually a zip file, which should be here on the desktop. Here's blah.zip. I can open that, and I'm stuck with, I'm guessing, is that blah? Yeah, there's my file. Okay. So, having said that, what is zipping? Okay, it's compressing. How does compression work in computers? And why is it important for networking? So kind of coming full circle to something we've been dealing with all semester and something we've been talking about even recently with our Rickroll file. The whole reason we chose to send that small file over the network was because it was small, right? It would fit. We weren't, actually, we were, unbeknownst to us, using a compression routine because wasn't it a PNG or was it a JPEG?
PNG.
Doesn't matter, both of them are compressed formats. Doesn't matter, both of them are compressed. Why might we want to compress data before sending it over a network?
Faster speeds and reduces the amount of bandwidth needed.
Okay, well, tell me about this faster speeds thing. It certainly reduces the amount of bandwidth because if I have an uncompressed file and I have the compressed version of that same file, what do we hope is true?
One smaller.
We hope that the compressed version weighs less, right? There's less stuff there. So for instance, you know, if we were to compress me, I'd probably weigh like $1.20. All right, so in any case, we compress stuff so that we can transport smaller packages across the internet, right? But when something's compressed, what are we going to have to do on the other side?
Uncompress it.
We have to uncompress it. Does that take time? Okay, so what we're doing is we're really trading time here for time here. We're deciding which is faster. Is it faster to run something through the CPU to decompress it? Or is it faster to send something over the network in an uncompressed state so that we don't have to do that with the CPU later on?
Also faster or cheaper.
Huh?
Also faster or cheaper.
Cheaper is fair as well. Typically in technology, those things kind of connect to each other, but I think that's fair. So, which is faster, our modern day internet connections or our modern day CPUs? By how much? Like a lot, right? It's not like a close race. Like I once saw this TV show. It was called Man vs. Beast, and they had an Olympic sprinter racing against a zebra. Name one other class where you can get onto that topic.
See, I almost thought it was going to be what's his Kobayashi versus
It was the same show, the same episode, but they had a Olympic sprinter versus a zebra in a foot race, and the zebra just destroyed him. Wasn't even close, but it was closer than this race would be. Okay, CPUs would be like an Olympic sprinter versus me. Okay, but I don't get up. Okay, and it's still probably not adequately comparing the two.
You're
CPUs.
running pretty fast to the battle hack.
I know. Did you like that? I have impressive burst speed. But man, it's like trying to stop a train. You gotta hit the brakes like way back. Yeah, the thing you was talking. You've seen the Kobayashi bear thing, right? Really? Oh, it's
Is it on YouTube? I think we should watch it.
no. We got stuff to do. I'll just tell you in 15 seconds. Well, you know who Kobayashi is. He used to be a professional eater. The guy who ate a zillion hot dogs. Well, it was back when he was #1 in the world for speed eating. They had him in the Man vs. Beast show go up against a grizzly bear. So they had Kobayashi, and I guess bears won't eat bread. So no buns. It was just hot dogs. So they had like 250 hot dogs on this platter, and the agreement was they would start eating when the bear started eating. And so Kobayashi's sitting there, his bear comes out, and he's just pissed. And they were both in separate cages, so he was safe. And Kobayashi starts mowing through these hot dogs like it's nothing, and the bear's like not even interested at first. The bear ate those 250 hot dogs in like 30 seconds. he was like going by just like almost like inhaling them, just with his, wasn't even using his paws, just breathing them in. It was awesome. It wasn't even close. And then the bear started like attacking the side of the cage because he wanted to get at Kobayashi's. He wasn't done. He was not done.
They should have had you go up against something.
Well, if Kobayashi can't beat him in speed eating, and I wasn't a speed eater, I was a distance eater, I can't eat as much as a bear, and I certainly couldn't eat as fast as a bear. So, yeah, I would lose. I guess it would be kind of funny. Although I would look a lot closer to the bear's size than Kobayashi.
You got the right bear, it'd be close.
All right, so that's kind of the purpose of pipes. Pipes connect streams together. All right, fair enough. And then sprinters, of course, can not beat zebras. So punchline with compression is we're trading off computation power on the endpoints for the data size during transport. Okay, so the less information we have to send, the better. Is everything compressible? How do compression algorithms kind of work?
Tip out.
Okay, if we're trying to invent our own compression algorithm, how does it kind of work? Well, let's think about, let's just think about a picture. So an uncompressed image would be like a bitmap, right? BMP. And how do bitmaps work? So if we're thinking is the early days of the internet, we talked about it before, we had the web pages and they're loading one line at a time type thing. Okay, so now we have this idea of a bitmap, uncompressed image. What is a bitmap?
Would each pixel have its own set of color data?
Yeah, so maybe we're using RGB color. Maybe it's 16-bit color. So we'll have 48 bits of data for every one pixel. And so if we have a 1024 by 768 number of pixels thing, so that's 1024 by 768, that's that many total pixels times 48 bits. That's that many bits divided by 8. That's bytes divided by 1024. That's kilobytes divided by 1024 is megabytes. So that's 4.5 megabytes for a 1024 by 768 uncompressed 16-bit color picture. All right, so how big is that same size image as a JPEG, do you reckon? So,
Kilobytes.
huh?
Kilobytes. Not a
Low kilobytes.
Yeah.
Low kilobytes. A lot smaller. So, how do you think those compression algorithms might work when you're dealing with bytes? Because at this point, it doesn't matter whether it's video or images. It doesn't matter what it is, because with computers, everything ultimately becomes zeros and ones. And if we're relying on the CPU on either side, well, the CPU on the first side is doing the compression. The CPU on the other side is decompressing it. Those guys have to agree upon a format. So if you just have a whole giant wall of zeros and ones, and I tell you to make that smaller, what might you do? What are things, you have zeros and ones to work with, very limited. Okay. On the other end, you have to compute the output. Okay, so really, you think of a zip file as being an executable, and when you run that, or we can look at it as an input, you run that through a unzipping program. That guy knows how to reassemble the original. You're not extracting the original from it. You're actually rebuilding the original. So if this was a transporter, we're getting a copy. So the original bits were destroyed. These are new bits that just happen to be in the same order as the old bits. Make sense? So really what they're probably doing is they're either taking strings of ones or strings of zeros and creating math formulas that allow you to recreate big strings of zeros and ones so that the math formula is this big and the zeros and ones were this big, so now you shrunk it down. Do that thousands of times, and now you have your data that used to be this big, now it's this big. Make sense? And then we have the CPU do the math problem on the other end. So that's compression. We dealt with writing data to another file. So here's a couple of libraries here that they're, so this is a file stream. This is the zip library. So they're creating two streams here. They're getting the read streams. This is like when we did Java. This is get input stream from our whatever we passed in, the argument from the command line. So this would be the file name, let's say. And then the out file, we're creating a write stream to write out to another file. This is the file we're writing out to. But when we have our in file, we're actually creating a pipe, just like we did before. So this is kind of the Node or JavaScript version. Kind of those are synonyms right now for us. This is the JavaScript equivalent of what we did right here. I'm reading in a file. This reads in the input stream, writes out the output stream. That's what cat does. So cat takes an input and writes it, spits it right back out. I'm piping that to the zip library, which ultimately creates a output file. All right, so that's what this is doing right here. We're taking our in file, we're piping it to the create zip gzip function, and then we're piping that to our out file. So this guy is sitting in between. Okay, have our two streams. In file reads in, pipes to zip, pipes to output file. Output file ultimately is the name of our zip file. Okay. So we've already dealt with readable and writable. Don't need to talk about them. Let's just go down a little bit. So duplex. I want to talk about duplex in general as it relates to networking first, then we can talk about it as it relates to streams. So we have two different things that we need to be concerned about in networking related to duplex. We have full duplex, and we have half duplex. How many of you have heard of either of these before? Do you know the difference? I think a couple weeks ago, didn't I hear Haxon make some duplex joke? I thought I heard Haxon make a duplex joke in one of the classes. After one of the classes he was here. So duplex deals with the direction that data flows on a stream. Okay? Full duplex means that data can flow in both directions at the same time. All right, so we can have water flowing downstream at the same time as it's flowing upstream. It's a real life relative impossibility. There's probably undercurrents that sort of kind of make that work, but it's not real common, right? Half duplex is data can flow in one direction at a time. No duplex means it only flows in one direction, period. Okay, so duplex is a multi-purpose stream where data is allowed to flow in both directions. And then within duplex, we have two versions. Is one necessarily better than the other? Right off the top of our, when we first hear it, you might say, oh, full duplex is better. Why would we ever use half duplex? So do you think half duplex came out first and then we figured out how to do full duplex and we just never used half duplex again? Go ahead.
Part of computers is communicating, so if you're talking at the same time someone else is talking to you, it's kind of, you have to get information to respond to information.
Okay, so there are tasks where half duplex makes the most sense, right? So if you and I are talking at the same time, you and I are going back and forth. If we're both talking at each other simultaneously, we're going to find it funny, but we're not going to be effectively communicating, right? Okay, so would it make sense then, even though we are operating on a full duplex channel, there's nothing that's keeping you from screaming at the same time as I'm talking, okay? Other than just our own manners, we're policing ourselves, right? But would it be appropriate for us to be on a half duplex channel, where right now I'm writing out to you, as soon as I'm done, now you can write back to me? Is that appropriate for human communication? It certainly would be. What's the benefit? In human beings, would we be able to put up with half duplex? When was the last time you were in a conversation where at some point one person didn't interrupt the other person? That's how human beings talk, right? Sometimes somebody says something and somebody interjects, asks a follow-up question or something like that, or just you have people just interrupt people all the time. Whatever it is, human beings really need full duplex because we have to be able to adapt to what's going on around us. But computers, not so much. In fact, computers, we might appreciate the idea of half duplex if for no other reason than it's self-policing. Think about our Java program that we wrote when we had our fake protocol going back and forth, where we were having to make sure, remember, we were kind of going back and forth between the two applications. This guy sends a request. This guy receives the request. This guy receives the response to the request. Back and forth, back and forth, back and forth. We were building the idea of half duplex into our logic of our program rather than just having a stream that was half duplex and having two guys just going at it, but the stream only allowed one of them to communicate at a time. And we can even have directional half duplex where it toggles back and forth between whose turn it is. So in our logic, we might say that it's this guy's turn to send something. Well, this guy can scream all he wants, but that's not getting sent down the stream because the stream is currently flowing this way. It might get buffered up there. TCP/IP would support buffering the data so that when the stream allows it to flow, then it would. But up to that point, the stream itself is policing the protocol, and that could be handy, right? What about speed? What's does a stream have a maximum speed? I mean, as far as we're concerned, what streams have we? Right, we have a stream running right now. I think I still have the server running, don't I? So I have a full duplex input-output stream running on the machine right now because we have a little Hello World server thing going. How fast is that stream? It's a local. I connect to localhost. I was over here on my web page and I hit localhost 8080 and enter. Fast. How fast? Is that infinitely fast? What dictates the speed? What's the speed limit on that local loopback? I can say localhost, or what else could I say? We talked about this before. 127.0.0.1. Okay, that's the loopback IP address. That's a non-routable IP address that loops back onto itself on network interface. So, what's the limiting factor for the speed of this? Yeah, the communication channels, the physical hardware streams that are created, that are connecting, in this case, our monitor to our to the computer, the computational motherboard, let's say, and then you have all the wires in the motherboard. So something's going to be the slowest out of all those, right? Okay, so as we try to do this communication, really probably the speed limit was how fast we can press enter. The human being was a slowdown in it, but realistically, it wasn't infinitely fast, but it was probably faster than if we had a dial-up modem running the server and it just happened to not be behind a firewall and we connected to that dial-up modem over in Moscow. There's going to be a much larger delay, correct? So punchline there, streams do have speed limits. There's a maximum bandwidth that a stream can hold, and it's not common to all streams, but every stream will have a maximum bandwidth. Well, sometimes we need to send really big data. We were talking about this a little bit ago with compression. So even if we compress a really, really huge file, so let's take a data file and compress it into an ISO. ISO is not a strong compression format, but it is a compressed format. Let's say we do that, and we're going to send it over the network. If we have a faster upload speed, will it transfer faster than if we had a slower upload speed? Our internet connections are full duplex. We can be sending stuff at the same time that we're receiving stuff, correct? We rely on that. Sometimes we are sending emails at the same time as we're downloading the latest Game of Thrones. Okay? Is Game of Thrones is on tonight, right? Last night, okay. I just had a web chat with a guy from Ireland, and he was just recording it now. So I guess that must be when it airs over there in foreign countries. When does it air in Brazil? Do you have Game of Thrones in Brazil? You do? You have Game of Thrones over? I didn't know. Same time as here? Really? Brazil Central Time?
About the same.
Yeah, that makes sense. So you don't even get jet lag when you fly home.
No, I mean, there's 2 hours, at least from my city. 2.
Oh, because you're in the east?
Yeah.
Or you're what? No, you're east. East. So you're like the same time as like the Bahamas, one of the Caribbean islands. 1 hour later than Florida.
Yeah, 1 hour later
The East Coast. Then New York, yeah. What was I talking about? Oh, Game of Thrones. We're talking about Game of Thrones, and we're talking about Ireland. And then we talked about Sprinter versus Zebra. Kobayashi versus Bear, correct. All right, so in any case, we do have a maximum speed, but if we're utilizing the entire bandwidth of the stream for one direction, we can move data faster. If we're using only part of the bandwidth of the stream, let's just say half, there's actually load balancing technologies that try to maximize the stream's maximum bandwidth for bidirectional communication, for full duplex communication. But if we only send stuff in one direction, we can send stuff faster. Make sense? So punchline here would be that there are times when half duplex is actually preferred, especially in computational solutions where we can control, there's logic to who's going to talk next, as opposed to human beings where we like that flexibility. Okay. So in Node, we can actually create our own streams. So there's streams that we ought to already think about. things that are associated with files, things that are associated with an application, something like that. But what if we want to write our own streams that can do stuff? Streams fall into two categories: readable and writable type streams. And then we have this general API. We'll probably look at this next time since we're just about out of time for reading and writing streams, and kind of look and see that it's kind of similar to what we've dealt with Java. Read byte, write byte, read string, write string, that kind of stuff. Okay, so we have ways of operating with these streams. But we can actually create our own named streams. Okay, in Java, we really are used to working with 3 streams all the time. We have system.out, that's our standard output stream. We have system.err, that's our standard error stream. So there's actually, on almost every operating system, there's 2 standard output streams. One is standard out, one is standard error. Okay, and both of those go out to the terminal, but you can actually work with them separately. And I realize we're out of time here. But if we were out here, I can redirect stuff to standard error and redirect something else to standard out. The difference is the standard out is the first output stream. Standard error is the second output stream. So when I redirect stuff, if I just redirect with just like that, it defaults to standard out. If I put a 1 before it, that is standard out. If I put a 2 before it, it's standard error. And then the other one is standard in. That's command line here. Okay? All right. Well, now that I showed you how to do Node on your local machine, do your homework that was going to be due today. Make sure it's done for Wednesday. We're going to come back and we're going to write our own streams, and then we're going to kind of connect those two together. All right. I'll see everybody on Wednesday.